morning, students. Today we are going to discuss the topic on symmetric groups, alternating groups and permutation groups. First we let capital A be a non-empty set and the set SCA of all permutations of a non-empty set A is a group for the product of the permutation and it is denoted by G is equal to SCA, composition. First here we are constructing for a non-empty set A we are constructing a permutation, the set of all permutations. We have to prove that this set forms a group under the composition of permutation. So we know that you take two permutations f and g belongs to SCA, then f dot g is equal to f composite g, that is also belongs to SCA. So therefore closure property is verified. And next we check the associativity property. Take three permutations f, g and h in SCA, then f dot g of h is equal to f composite g of h, this is equal to f composite of g composite h, this is equal to f of gh. So therefore we have proved that fg of h is equal to f of gh, therefore associative property is verified. And we see that identity permutation is an identity element. So therefore name this identity permutation as IA and this belongs to SCA. So then f dot I will be equal to f composite I equal to f and I dot f is equal to I composite f is equal to f. So now next we check the inverse. So let us take a permutation f belongs to SCA, then f inverse also belongs to SCA, and we composite f with f inverse, we get f composite f inverse is equal to f inverse composite f equal to IA. So since SCA satisfies the four properties closure, associativity, identity and inverse property, SCA is a group under the composition of operation. So and it is called the permutation group. This group is called the permutation group. Next we define symmetric group. So definition: the group of permutations of a set 1, 2, 3 is called a symmetric group of symbol 3 and it is denoted by S3. Next we define symmetric group. The group of permutations of the set 1, 2, 3 up to n is called a symmetric group of degree n and it is denoted by Sn. The number of elements in this group is equivalent to n factorial. Therefore order of Sn is equal to n factorial. So this is a general formula. With this we can find the number of elements in S3 is equivalent to 3 factorial, that is equal to 6 elements. Now we give example for the symmetric group of symbol 3. Let the set A consists of 3 elements 1 to 3. Then there are 3 factorial elements. Here the elements are permutations. So here we define the permutations as rho naught equal to 1 mapped to 1, 2 mapped to 2 and 3 mapped to 3. And rho 1 is equal to 1 mapped to 2, 2 mapped to 3 and 3 mapped to 1. And rho 2 we define it as 1 mapped to 3 and 3 mapped to 2 and 2 mapped to 1. And mu 1 is defined as 1 mapped to 1, 2 mapped to 3, 3 mapped to 2. And mu 2 is defined as 1 mapped to 3, 3 mapped to 1 and 2 mapped to 2. Mu 3 is defined as 1 mapped to 2, 2 mapped to 1 and 3 mapped to 3. So therefore S3 consists of 6 permutations, namely rho naught, rho 1, rho 2, mu 1, mu 2 and mu 3. Where rho naught is called the identity element and it is identity permutation because here the element map to itself. Here we see that the mapping is like this: 1 mapped to 1, 2 mapped to 2 and 3 mapped to 3. Likewise you have to see here 1 mapped to 3 and 3 mapped to 1, then 2 mapped to 2 itself. So the element rho naught, the permutation, identity permutation rho naught is defined by I. Rho 1 is defined like this: 1 mapped to 2, 1 mapped to 2, 2 mapped to 3 and 3 mapped to 1. So it shows that 1, 2, 3. Here we have written it forms a cycle. So row 1 forms a cycle 1 2 3, and similarly we can row 2 forms a cycle 1 3 2, and mu 1 forms a cycle 2 2 3 3 2. So 2 mapped to 2, 2 and 3 is a cycle, 1 mapped to 1 itself. And here mu 2 form a cycle 1 3 and 3 1, 1 3 and 3 1. Here 2 mapped to 2 itself. Similarly mu 2 is form a cycle 1 2. Now we are finding the composite table for this permutations. So totally we are having 6 permutations are written in the vertical line, and another 6 permutations are written in the row wise. So we are mapping we are compositing one two three is mapped with I, you will get. So now whenever the permutation is composite with identity permutation, you will get the same permutation. So therefore 1 2 3 will be mapped to 1 2 3 mapped to 1 2 3, 1 3 2 mapped to 1 3 2, and 1 3 2 mapped to 1 3, 2 3 mapped to 2 3, and 1 2 mapped to 1 2. So similarly here from the we can frame the permutation as example, when 1 2 3 is mapped to 1 3, you will get the final answer will be equivalent to 2 3. So here from the composition table we see that the inverse of 1 2 3 is 1 3 2. Here the inverse of 1 2 3 is 1 3 2. Because while you are when 1 2 3 is permuted with 1 3 2, we will get identity permutation. So therefore inverse of 1 2 3 is 1 3 2. Similarly we can find the inverse of 1 3 is 1 3, inverse of 2 3 is 2 3, and inverse of 1 2 is 1 2. So here except 1 2 3 and 1 3 2, the other permutations are own itself, own inverse. So therefore the inverse of 1 3 is 1 3, inverse of 2 3 is 2 3, and inverse of 1 2 is 1 2. They are self inverse elements. So now therefore S3 consists of totally 6 permutations that we have already seen it. Now order of S3 is equal to 3 factor, which consists of 6 elements. So now we get the number of elements of order 2. Now totally we are having 3 permutations of order 2. See here. The 3 permutations 1 3, 2 3 and 1 2. In each permutation the number of elements is 2. So therefore we are having 3 permutations of order 2 and 2 permutations of order 3. The permutations are 1 2 3 and 1 3 2. So next we find the number of R cycle in Sn is equal to NCR into R minus 1 factorial. This is the formula for finding a cycle in the permutation. So now to find the number of elements in S3, so now first we find the partition of 3. The partition of 3 can be written as 1 plus 1 plus 1. So we are getting cycle of length 1. Totally the I will be the identity permutation. Here 1 mapped to 1 itself, 2 mapped to 2 itself, and 3 mapped to 3 itself. So therefore we are having 3 different cycles of length 1. And the possible chances of the partition are 1 plus 2. 1 plus 2 represents Actually, the partition is framed with the help of the condition a1 less than or equal to a2 less than or equal to a3, and plus and one more condition a1 plus a2 plus a3 must be equivalent to the order of the permutation. Here the order of the permutation is 3. So Sn. But here without violating the conditions, we can frame the three partitions 1 plus 1 plus 1 and 1 plus 2 and 3. The second term must be greater than or equal to the first term. Like with this we are with the condition, with this condition we are following the partition. So therefore in this case 1 plus 2 represents we are having a cycle of one length, that is namely A, and a cycle of 2 length equal to B.Sc. And similarly cycle of 3 length means A.B.Sc. Now I is the only one element. So now here B.Sc is the 2 cycle. So therefore we are finding the number of R cycles is formula. With the help of the formula we can find the number of cycles. For example, number of finding the 2 cycles is we apply the formula n equal to 3 and R equal to 2. So 3C2 into 2 minus 1 factorial. So 3C2 is 3 into 2 by 2 into 1 and 2 factorial is 1. So finally you will get 3. So therefore we can frame 3 permutations of cycle 2. And similarly ABC is 3 cycle. So now here n equal to 3 and R equal to 3. So therefore 3C3 into 3 minus 1 factorial equal to 1 into 2 factorial equal to 2. So therefore we can frame 2 permutations of order 3. So now while we are adding these 3 terms 1 plus 3 plus 2, we will get finally 6. That is total number of elements in S3. Now next we define the alternating group. The group of even permutations is called the alternating group. The set An, and it is denoted by this letter capital A suffix n. The set An of all even permutations of degree n is a group, so it's consisting of n factorial by 2 for the product of the permutation. So actually here number of odd permutations and number of even permutations are equal. That is n factorial by 2 elements will be in the odd permutation and even permutation. The formula for number of R cycle in Sn is equal to NCR R minus 1 factorial. So this is repeated again. So here we define the alternating group. Group of even permutations. The set An of all even permutations of degree n is a group of n factorial by 2 for the product of permutation. For here we show that the set of even permutations form a group. So we can define the closure property, associativity and identity and inverse property. The product of the 2 even permutations is again an even permutation. So therefore the closure property is verified. If f belongs to An and g belongs to An, then f dot g equal to f composite g, which is also belongs to An. And check the associativity easily. Take 3 permutations fgh belongs to An, then f of gh is equal to fg of h. The associativity property is verified. And check the identity permutation is an identity element. Inverse, let f belongs to An, then there exists an f inverse belongs to An such that f dot f inverse is equal to I, which is also belongs to An. So therefore the set of all even permutations form a group under the product of permutation. But the set of all odd permutations is not a group. So let Bn be the set of all odd permutations. Now we know that the product of the 2 odd permutation is an even permutation, so which is not an odd permutation. So therefore f belongs to Bn and g belongs to Bn imply f dot g equal to f composite g does not belong to Bn. The closure property is not verified. So therefore the set of all odd permutations is not a group under the product of the permutations. So we give the example for the alternating group A3. A3 is called the set of all even permutations of 3 symbols. So we know that 6 permutations exist of 3 symbol, namely the permutation is S3 group again, I 1 3 2 1 2 3 1 2 1 3 and 2 3. Here the permutations 1 2 1 3 2 3 are the odd permutations. So here the set A3 of even permutations on symbol 3 is I 1 2 3 and 1 3 2. So therefore A3 is equal to I 1 2 3 and 1 3 2. This is a set. Now order of A3 is equal to number of elements in the A3 equal to 3 factorial divided by 2. 3 factorial is 6 divided by 2 equivalent to 3. Here the set A3 of even permutations on 3 symbol is 1 to 3 is how it is obtained. There is a shift to 2 shifts are available. 1 mapped to 2 and 2 mapped to 3. There are 2 shifts. So therefore it is an even permutation. Here Sn is the non-abelian group for n greater than or equal to 3. Suppose the value of 3 is n is 3. We get an S3 group. S3 group is the first group which is non-abelian. And also product of the two permutations may or may not be commutative. Now An is a alternating group for An is a non-abelian group for n greater than or equal to 4. So Sn is the set of all permutations, An is the set of all alternating even permutations. So An is non-abelian group whenever n greater than or equal to 4. And Sn is non-abelian for n greater than or equal to 3. Next we define permutation group or symmetric group. So a permutation of a finite set capital S is a bijection from S to itself. That is, we take a finite set S, we define a mapping F which is 1 to 1 and on to from S to S. Then we call it is a permutation. Now let S be a finite set of n elements. So therefore S consists of elements A1, A2, A3, An. The permutation F can be written as A1 is mapped to F of A1, A2 mapped to F of A2, etc. An mapped to F of An. So let S is equal to the set consisting of 4 elements 1, 2, 3, 4, and F is a mapping defined from S to S, where F of 1 equal to 2 and F of 2 equal to 3, F of 3 equal to 4 and F of 4 equal to 1. Then the permutation F can be written as the domain and the corresponding codomain elements must be written against the domain element. 1 mapped to 2, 2 mapped to 3, 3 mapped to 4 and 4 mapped to 1. Now equality of two permutations we discuss. Let F and G be the two permutations, then they are called equal if and only if F of A equal to G of A for every A belong to S. That is, image of every element of S under both F and G are equal. And identity permutation. Let S be a finite set of n elements, then a permutation F is called identity permutation if and only if F of A equal to A for every A belongs to S. That means the element must map, the image of the element must be same. So now here example, let S is equal to A1, A2, A3, An. So the image of 1 is F of A1, image of 2 F of A2, image of 3 F of A3, etc. image of n F of An. This is called the I5, In, Is. Now I equal to 1 mapped to 1, 2 mapped to 2, 3 mapped to 3, 4 mapped to 4, which is represents the identity permutation. So here next product or composition of permutations we are seeing. So let us take two permutations F and G of a non-empty set A. Then the product of the permutation is also a composition of permutation. F dot G of X is equal to F composite G of X. This is equal to F of G of X. Now here we take the permutation F as F is mapped to 2, 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 4 and 4 is mapped to 1. And here G is mapped to 1 is mapped to 3, 2 is mapped to 4, 3 is mapped to 2 and 4 is mapped to 1. So now we are finding the F dot G of X. F dot G of X is equal to f composite g of x, this is equal to f of g of x. Now f composite g of 1 value equal to f of g of 1. But g of 1 is nothing but the value is here, g of 1 is 3. So we write here, and f of 3 we find the image of 3 under f. So f of 3 equal to here it is 4. So therefore final answer will be equivalent to 4. Therefore the image of 1 under the composition f composite g is 4. Similarly, we can find the f composite g of 2. F composite g of 2 means g of 2. The image of 2 under the mapping g is 4. You write here 4. Then f of 4. So we find the image of 4 under f. This is equivalent to 1. So therefore f of 4 equal to 1. And similarly we can find the f composite g of 3. This is equal to f of g of 3. The value of g of 3 is 2. So therefore we have written here f of 2. Value of f of 2 is 3. So therefore the final f composite g of 3 is equal to 2. And similarly we can find f composite g of 4 equal to f of g of 4. The value of g of 4, the image of 4 under g mapping is 1, f of 1. So the image of 1 under f is 2. So therefore here the final answer will be 2. Now finally we have written the values, the composition permutation f composite g as the image of 1 is 4, the image of 2 is 1, image of 3 is 3, and image of 4 is 2. So similarly we can find the value of g composite f also. Here g composite f of x is equal to g of f of x. So likewise in a similar manner we can find the value of g composite f as 1 mapped to 4, 2 mapped to 2, 3 mapped to 1 and 4 mapped to 3. So next we define the cyclic permutation or cycles. A permutation sigma of a set capital S is a cycle permutation or a cycle if there exists a finite subset a1, a2, a3, an of S such that sigma of a1 equal to a2, sigma of a2 equal to a3 and sigma of an equal to a1. That is the image of the first element and the image of the last element will be same. Here sigma of a1 and sigma if suppose the image of x is itself, sigma of x is equal to x for every x belongs to S, then x does not belong to the cycle a1, a2, a3, an. Then we can write a cycle permutation sigma as sigma equal to a1, a2, a3, etc. an. Now let us see an example. Let f is equal to 1 to 3, 1 mapped to 4, 2 mapped to 1, 3 mapped to 3 and 4 mapped to 2 be a permutation. Then we can write a cycle. Here f of 1 is 4. We see that f of 1 is 4, f of 2 1, f of 3 3, f of 4 2. So therefore 1 mapped to 4, 4 mapped to 2 and 2 mapped to 1. So we get a cycle of sigma consisting of a cycle 1 4 2 and 3 mapped to 3 itself. And similarly 3 does not belong to here in this cycle 1 4 2, 3 does not belong to sigma of 1 4 2. Let S is equal to 2 4 5 6 belongs to S3 be a we consider a cycle 2 4 5 6 belongs to S6. Now here sigma of 2 equal to 4, sigma of 4 equal to 5, sigma of 5 equal to 6 and sigma of 6 is equal to 2. So therefore here the self image does not contain in a cycle. that is 1 mapped to 1 and 3 mapped to 3 are the self image. These self images will not appear in the cycle. Here the element self images of 1 and 3 does not belong to the cycle 2, 4, 5, 6. Here sigma of 1 equal to 1 and sigma of 3 equal to 3. Finally, we can write the permutation sigma as 1 mapped to 1, 3 mapped to 3 and 2 mapped to 4, 4 mapped to 5, 5 mapped to 6 and 6 mapped to 2. Thank you.